So let's get started with a welcome. And the first person to welcome us is Omololu Akin Ojo, who is the director of the East Africa Institute for Fundamental Research. Omololu.
Yeah, thank you, Richard. So let me share my screen. And I have my presentation. And if I can make it presentation. Okay. So good morning to many people, and good afternoon to some, and good evening to a few others. So I'm welcoming you to this workshop of the US-African Initiative in Electronic Structure. As some of you know, we already had a short kickoff program in March online, and this is the first major workshop that we're having. And we'll be having another one next year in the US. Okay. So I'll just give you a few words to welcome you. So I'm glad many of you are here. I'm glad many of you will be here throughout the week also to present different things. So at the workshop at the kickoff that we had in March, this is a screenshot of the kickoff, and it's interesting because already you see a lot about what this program is about, what this USAfri program initiative is about. So on this screen, you see a picture of many of us and from different parts of the world and working together in this workshop. The main thing we want to do with this USAfri initiative is to increase collaboration between researchers in the US and researchers here in Africa. So first, so I give a quote from Ricardo Hausmann. He was the former director of the Center for Immigration and Development at Harvard University. So he said that the secret to prosperity is technology, but technology is expressed in three kinds of elements. It's expressed in tools or equipment, codes or prescriptions, and know-how or tacit knowledge. He claims that the first two, while tools and prescriptions are easy to disseminate, so you can just buy the equipment. You don't have to do a lot, you can buy the equipment. He claims that know-how is hard to spread, okay, because it is acquired slowly through imitation and repetition, in the same way that we learn to walk or learn a language as children. Nobody learns to play a sport or diagnose a patient by reading about it. It requires years of experience. So what we want to do, the main thing we want to do with US-African Initiative is to build collaborations that can help us everywhere to gain the know-how and the knowledge that we need. It's one thing to have the code or the equipment, it's another thing to know how to use them properly. So through collaborations, we expect that the US-African Initiative will help help us in sharing tools and equipment, basically computational resources. It will help us in sharing codes also. And we'll be able to build collaborations that will help us to build the know-how and the tacit knowledge that we need. Later on, during the program, we'll talk to you about peer groups that can help us to build the imitation and repetition that we need to learn how to learn the things that we need for knowledge transfer and technology transfer. So again, the main thing we aim for in this US-African initiative is to have collaborations so that there will be more people with know-how all over the world. Africa has lots of young people, and this lots of young people can gain the know-how that they need. US has lots of computational resources, so we can share and collaborate in different ways. So this is the main aim of the US-African initiative. I took this slide from the one that we did in March 2021, but the details are still very correct in the main part. So the workshop in Africa that was supposed to be held in June 2020 is the one we're having now, has been shifted to June 2021. We plan to have a workshop in the US in 2022 in the summer. It may not be exactly June, but in summer of 2022. And then following that workshop, there will be African researchers that will visit and work with US researchers in that period also. So this is what we aim for to help us to have a lot of collaboration between US and Africa. There'll be sharing of computational resources from US partners also. This peer program is something that Richard may speak about later on, where we care with different people so that we can have a lot of collaboration. The collaboration will solve the problem of isolation that we have in Africa, where scientists are working alone in different parts of Africa on different problems. It will also solve the problem in which we have limited training, where scientists don't have enough know-how or tacit knowledge that is needed for advancement and a lot of technology. So I will just summarize the program that we'll be having. As you know, is an online workshop. It extends from Monday to Friday. If you are in Africa, in the Central African time zone, GMT +2, is 3 p.m. to 6 p.m. If you're on the East Coast in the US, is 9 a.m. to 12 noon. It's roughly this way. So I'm just asking that you dedicate this 3 hours every day to this program. Roughly is this way. There's a keynote that lasts for about an hour. There are 4 short talks, and then there's a poster session. And then after this, there are discussions. You don't have to run away after the discussion because I asked for 3 hours. But during this discussion is a good time to meet with people and talk about possible collaboration that you can have with them. So my last word now will just be to welcome you to this workshop. And I hope we all make the best out of it by getting a lot of collaboration, that's as much as we can, collaboration and learning new things as much as we can. So I stop here and I say thank you and welcome again.
Thank you, Omololu. So next in the welcoming is Renato Winskovic. She's the person that's really got this going. So Renata, you're muted, Renata.
Hello, everyone. Let me share my screen.
Okay, it's working.
Just a minute, just a minute. I am sharing. I'm sharing. Okay.
Yes.
Now, I cannot. Just a second, please. Okay. Good morning. Hello, everyone. I am okay. Let me. I am Renato Winskovic, one of the 4 PIs of the USAfrI initiative in electronic structure. You heard from Omololu, and you hear from Sinead and Richard Martin again after. Well, the USAfrI initiative was one of the 4 inaugural awards of the APS Innovation Fund launched in 2019. This award was established to support the APS vision and mission in line with the society's strategic plan. You can read a lot more about the strategic plan online if you Google APS strategic plan. It's interesting reading. But here are the 4 pillars of the APS mission. 2 of them are aspirational and 2 are foundational. So the first 2 are to serve its members, the physics community and the society at large, and to ensure a meaningful role in scientific research dissemination. And the USAfrI initiative supports these 2 pillars. The foundational pillars consist in increasing organizational excellence and securing financial stability of the society. So USAfrI, USAfrI short for the initiative, was established to create a platform for exchange of Africa and US physicists and create opportunities to impact research and education in Africa. Of course, electronic structure was a natural choice because it has applications in many fields and because it taps a network of interactions in Africa that has been sustained by efforts for over the past 10 years, the ASISMA, the African School of Electronic Structure, Methods and Applications. Richard will tell you more about it right after. The workshop, the proposal consists in 2 workshops, one in Africa, in Kigali in 2020, and one in the US in 2021. And for obvious reasons, it's happening now virtually. And next year, Columbia University and New York City will welcome our colleagues from Africa, and they will, their participation in the workshop will be followed by visits to research groups and user facilities in the United States. The program was not delayed exactly by 1 year because APS got an extra from us, a mini workshop that happened in the March 2021 March meeting and launched the peer program of bilateral interactions that has already started. So Richard will tell you, and Sinead and Richard will tell you more about ASISMA. Thank you. Welcome to the workshop.
Right. Thank you, Renata. So Sinead is going to start. She's a special person for USAfri.
Great, thanks, Richard. Okay, so thanks, Renata. So just so everyone's aware how USAfri fits into the collaborations and connections we've already been establishing throughout Africa. These are the particularly important supporters and partners that we've had in developing the USAfrica initiative. Of course, it wouldn't be possible without the APS Innovation Fund, but we've also developed a very close connection with Omololu and the ICTP-East African Institute, which is really the center of networking and connectivity within Africa for us for this initiative. We've also been working with the National Society of Black Physicists to disseminate knowledge of USAfri throughout the US, in addition to really building on existing connections through ASESMA and through the African Light Source. And so I'm going to briefly tell you a little bit about ASESMA if you don't know about it already. ASESMA is the African School on Electronic Structure, Methods and Applications, and it was its first school was actually in 2010 in Cape Town. So there was a preschool 2 years prior, but the first official ASESMA school was in Cape Town in 2010. And the aims of ASESMA are to really do what Omololu highlighted as being one of the needs for African physicists, which is to disseminate and share this knowledge, particularly in the electronic structure community. So the plan for ASESMA is to have a biannual workshop. We had a follow-up in Kenya in 2012. We had one in Johannesburg in 2015, in Ghana in 2016, in Ethiopia in 2018. And we just finished on Friday our AID 2020 workshop, which happened on Zoom. So I'll hand this over now to Richard to give you a little bit more information about ASESMA.
Thank you, Sinead. I hope I can share screen properly.
Okay.
Oops. Okay, now I'm sharing the wrong screen. Is that good? I can't see myself.
We can't see your screen yet, Richard.
Oh, the host is, I can't be seen. Sorry. Can you hear me?
Yes.
Okay, so and sorry. Oh, I got the wrong slide. Oh, I'm sorry. Okay, everyone, it's me going too slow. There. Now let's see if I can present from this slide. Okay, I may have to go. Okay, now is it showing? So I wanted to say that ASESMA
it's not showing yet, Richard.
Okay, I'm sorry. I'm showing. I'm highlighting my screen.
I have. I think a version of your slides. If you want me to share my screen, the version from yesterday.
Please. I'm sorry.
Yeah.
Okay. So now I'm gonna lower. Okay. Very good. Thank you, Sinead. ASESMA is an ongoing series, as has been already described. And I'd just like to say it was supported by the IUPAP for 10 years, which was really quite remarkable from the start. That it would be every 2 years, and the goal was to build up collaborations. And it needed to be a continuing series in order to do that. And it has succeeded in creating a network of active scientists in Africa. And there have been more than 200 participants from 22 countries during this time, and several groups have built up, and it's really okay. And we want to emphasize that USAfri is different. It's building on the network. It's not a school, it's to bring together people who work together. Next slide. So I just want to mention the peer program, and the start for this really was the tutors and mentors for the assessment school. They have grown up and together, and they were really the foundation of the way the school worked, because they worked together. So the corresponding thing in USAfri is the peers, young people who can work together across the miles. And I just believe this can be hugely rewarding. And sign up on the USAfri website. I mentioned that Sinead is a special person. She has been with the US with an assessment program for the entire time, and she took responsibility, and she is one of the leaders of assessment and USAfri now. Next slide. So this is welcome to the workshop for USAfri. It's exciting to be part of something really new, because electronic communications provide opportunities. Then we have a larger workshop than we had before, than we would have had if we were in person. So now we actually have something that makes it possible for people in more isolated places. And so let's take advantage of it. Let's make it happen. Look forward to 2022, where hopefully we can in person, but also bringing together people electronically. So thanks to everyone for the welcome, and we should move on to the program. Okay, I see myself in the window, so I will call on the first speaker, who is first speakers, right? Is Elif Ertekin from the University of Illinois at Urbana-Champaign. She's in the School of Mechanical Science and Engineering, and I think she will introduce that she is giving the talk along with African researchers that she's working with now. Elif?
Okay, great. Thank you, Richard. Let me just quickly share my screen here. Okay, is this visible to everybody?
Yes, we got it.
Yes.
Great, excellent.
Good.
Okay, perfect. So, okay, all right. So first of all, good morning, good afternoon, good evening to everybody here. Let me first say thank you very much to the organizers for inviting us today to present about our new collaboration. This presentation today will introduce the new collaboration that we have together with myself and a couple of our partners that I will introduce in a minute here. And let me just start also by saying thank you very much to Richard, who introduced this group here that is presenting today. Okay, so here's the outline. Today you'll actually hear from three of us, including myself. Both the African side and the US side will introduce some of our previous work, and then we will describe some of the plans we have for our newly started collaboration together.
Elif, you're not on presenter view, I think, so it didn't move on to the next screen.
Ah, okay, give me 1 second. Let me try again. How about this? Still no.
It moved on to the next slide, but we can see all of your slides on the left-hand side. But it still moved on to the next one, so.
Oh, it's not showing presenter screen.
Right.
Right.
Let me see if I can fix that. Play from current slide. How about now?
It's not sharing.
Share screen.
Start slideshow.
Is it sharing now?
It's sharing, yeah.
Sharing. But
And if I move to the next slide, does it update, for example, now?
No.
No.
Huh. Okay.
Are you in slide mode, share slide mode?
Yes, I am.
Might be the wrong screen that's shared. So maybe it's sharing the background screen.
You need to click from play from start.
So let me share again. So the problem is when I am.
From your screen, you can click a presenter mode. From your screen, presenter mode is shown there.
Okay.
Move up.
So how about now? You are seeing everything?
There is a menu for presenter view.
Yeah.
Move up.
Do you see? Can you see this now?
Yes, move to the left. There is a menu for presenter view. Yes, that's the click it. Yes.
How's this? This.
Yeah, that's it.
it's okay. We can see it.
Oh, that's presenter mode.
Yeah. Maybe what I can do is, let me try.
Maybe share after you put it in the full screen.
So if I do this slideshow. If I show it this way, the trouble is when I'm going into presentation mode, but I think what I can do is just directly share like this. Is this okay for everybody?
Yeah.
Okay.
Yeah, this is great. Yeah.
Yeah,
Okay.
it's fine.
Okay, I will go this way.
Yes, good.
Okay, all right. So this is our team, and let me quickly introduce everybody. So we have many of us here today. So we have Ibrahim Adetunji from Bells University of Technology in Nigeria. We have also Winifred Meng'wa from Egerton University in Kenya. Ligia Gomez is a postdoc here at Illinois with me, and you can see we have our new 11-day-old member of our collaboration, Joao, who joined us for a meeting last week. And then we have also Jonah from ICTP, Jonah Magura, myself, and Gboyega Adebayo from the Federal University of Agriculture in Nigeria as well. Three of us will be speaking today, as I mentioned. That will be myself, Ibrahim, and also Gboyega. Okay, so at this point, let me pass the microphone to Ibrahim. I think he will introduce what we'll be speaking about, which is thermoelectric materials.
Thank you very much, Elif. I welcome everybody. As Elif said, my name is Ibrahim. From Nigeria, particularly from Bells University of Technology. Actually, I would like to tell us a brief concept or a layman definition of what thermoelectric is. Thermoelectric is a concept, but how does this concept has value to the world? We know that a lot of energies are being utilized on a daily basis all over the world, and these energies are lost in form of waste heat. So the question is, this waste heat, how do we make use of it? Do we allow it to just be there and continue to pollute our environment? So concept comes that this thing can be converted into light, but how? So you can see the picture. So from all these gadgets, laptop, engines, fridge, power plant, cars, so they produces heat. When this heat passes through converter, we are sure of getting light. But this converter based on a technology called thermoelectric. So on the layman concept, thermoelectric is the conversion of waste heat into usable electricity. Next slide. So now, when you now talk of thermoelectrics, so the converter in the previous slide actually involved this thermoelectric module. So the thermoelectric module consists of the heat source and the cool side. So it's just a kind of a two-way concept in which when you have difference in temperature, you generate electric voltage. And when you have difference in voltage, you also generate temperature. So these concepts give us what we know today as thermoelectric principle. But materials that can be used for this type of things needs to satisfy some conditions. So materials that can be used require a very large figure of merit for it to be efficient. So, and the figure of merit depends on the power factor and the lattice thermal conductivity. So for us to be able to have a very good and efficient materials to give us good figure of merit, the materials that are going to be used must have a very large power factor and at the same time has a very low lattice thermal conductivities. A take note is that in current thermoelectric devices that are being used these days, one thing is that it is inefficient when the figure of merit is about 1. That is, when the value is around 1, so the production will be very limited. And also, it will be able to recover waste heat when the figure of merit is 2. So based on this concept, I would like to pass over to Professor Adebayo to give us a brief insight into what we have been doing on materials that can be used in this area.
No, thank you very much, Bamidele. And let me start by thanking the organizer for the opportunity to speak here. And I will also want to thank Professor Richard Martins for bringing us together. Actually, this collaboration started about 3 months ago, yeah, when Richard assembled all the team members. So this afternoon, I'm going to talk about what is called Oscillate Power. Well, the overview of what I'm going to say, can you move back to a slide, Winnie? Can you move back a slide? Slide 7. Okay, thanks. The overview of my talk is I'm going to talk about what constitutes Oscillate compound, and I'm also going to tell about the structure and also to tell about thermoelectrics. I will also shed light on what makes Oscillate alloys to be good thermoelectrics. Next slide. Let me give you a definition of Oscillate compounds. As we all know, these are special compounds that are magnetic in nature. However, the constituent elements are non-magnetic. So this is a short definition of Oscillate compounds. Now, if we look at the periodic table, which is on the screen now, if we partition it into the 3 colors, X, Y, Z, these are red, blue, and green color. A combination of X, Y, Z will actually form Oscillate compounds. And of course, we have 2 types of Oscillate compounds. We have the full Oscillate, and then we have the half Oscillate compound. Next slide, please. Next slide. The structure of half Oscillate compound is a C1b structure, which actually is the, if we put all the atoms on the site of a BCC, it's actually form a half Oscillate compound. Next slide. Next slide, please. Maybe I turn off my video because my internet is actually slow from this end. So what do we note about thermoelectrics? Just a few moments ago, Bamidele mentioned the importance of the figure of merit. Actually, the figure of merit of a material actually determines its efficiency. So what we are saying is that if we have a high figure of merit, we are going to have the probability of such a material being a good thermoelectric. Now, another important factor is what is called the power factor. Now, these two quantities, the power factor and the figure of merit, have the important quantities, which are the Seebeck coefficient. Also, we have the electrical conductivity, thermal conductivity, and temperature. All these plays important roles in a material being a good thermoelectrics. Now, coming back to Oscillate alloys. Oscillate alloys are very good thermoelectrics because they possess great electrical properties. Apart from this, they are very stable thermally at high temperature. And also, if we are talking in terms of doping, is actually very to manipulate them so that we can have very high figure of merit. Now, one important thing that we have noticed in our research is that usually not all Oscillate compounds are good thermoelectrics. But if we look at the 18 valence electron counts compounds and also the 19 valent electron count compounds, they are actually very good thermoelectrics. Next slide, please. Next slide. Yeah. So as we have just said, there are many ways we can calculate the thermoelectric properties of Oscillate compounds. But if we want to calculate properties such as effective mass, the questions arise as to where do we do the calculation or the computation of the effective mass of an Oscillate compound. Is it in the conduction band or is it in the valence band? So the answer to this actually lies in the influence of power factor, because if we actually compute the power factor against different energies or against the chemical potentials, we will actually know the peak very close to the Fermi level where we can actually calculate the effective mass from. Next slide. In the next few slides, I'm going to share with us just a few things we have done on Oscillate compounds. Next slide, please. Now, in the first example, it is a work which we actually did in 2019, but was published in 2020. This actually, we look at the lattice dynamics and the thermodynamic properties of Oscillate compounds. Of course, we actually hope to go into doping this such that we can actually see how to increase the figure of merit of this compound. And also, lastly, I will show an example of a recent work which we did. In this particular work, next slide. Yeah, in this particular work, we actually work on the thermoelectric properties and also the mechanical properties of some oyster-like compounds. And let me say this, all these computations that we have done, they are things that actually we can do on a small laptop, on a computer. But in actual fact, we are hoping that this new collaboration with Professor Ertekin and our group will actually lead to the team from Africa having access to large computational facilities whereby we can actually look at large supercell such that we can see the effect of how to improve the figure of merit of some of these oyster-like compounds. And in addition also, it is our belief that this collaboration will actually also lead to joint supervision of doctoral candidates between the Africa and the US team. At this point, I would like to pass the mic to Elif, who is going to continue with the talk. Thank you very much.
Okay, great. Thank you, Adebayo. So let me next describe some of the previous work that the US side of the collaboration has been involved in for the last few years. So we are part of a team that includes computational and experimental researchers with the goal of demonstrating computational screening approaches to identify new thermoelectric materials. Our main experimental collaborators are Eric Toberer's group at Colorado School of Mines. And then this picture here conceptually illustrates the approach that we've been taking, which operates somewhat like a funnel. So we start with a large candidate set of materials, and then we screen them, trying to use computation in an efficient manner to determine which ones may be good options to try to synthesize in the lab for thermoelectrics. So in each step of this funnel, we evaluate an important material property or parameter for a thermoelectric, and then we pass on the best candidates to the next level. So this funnel here labeled intrinsic, we assess the intrinsic properties of each material, essentially whether we believe it has a chance of exhibiting a high ZT. And then the second funnel is the most recent one that we added, which is assessing the dopability of the material, which I'll try to show has turned out to be an important parameter for us. So I'll describe both of these two funnels in the next two slides here. So computationally predicting the quantities that go into ZT is challenging. So since these quantities, electronic and thermal conductivity, as both Ibrahim and Adebayo have already described, they're difficult to directly compute in an easy or straightforward manner. However, a couple of years ago, Eric and his collaborators showed that it's possible to estimate ZT through this alternative proxy parameter that we call beta, which the thermoelectric quality factor is how we refer to it. And this parameter beta is a model for ZT based on semi-empirical transport models for electrons and phonons to obtain carrier mobilities and thermal conductivity. I say it's semi-empirical in that it has been fitted to a large experimental data set across a chemically diverse set of compounds. But with those fitted parameters, the remaining parameters that need to be determined for a given material are based on readily computable quantities. So for example, the density of states effective mass, elastic constants, the volume of the unit cell. Although I don't go into details here, they are given in this paper here. The main point is that this quality factor beta enables us to do a high throughput and initial computational screen to try to identify promising materials, which can then be considered in more detail for further analysis. So this plot here shows compounds marked with their estimated values of thermal conductivity on the x-axis and electron mobility on the y-axis. Good thermoelectric materials would be up here in the upper left. And then compounds are colored according to their band degeneracy. And then the size of the circle indicates the estimated value of this quality factor beta. So large circles correspond to good candidate materials. So the main idea is that by using beta, it's relatively easy to try to identify thermoelectric material candidates. In the past, it's been used to rediscover many already known thermoelectrics and has also predicted several new ones that have since been verified in the lab. Okay, so let me now move on to dopability, and that was the second point of our funnel. Although this quality factor beta proved to be an effective descriptor of a semiconductor's thermoelectric potential, a new bottleneck actually quickly emerged for us in our work, and that was related to the dopability of the semiconductor. And the reason for that is that this quality factor beta actually neglects semiconductor dopability. It assumes that the semiconductors identified can all be doped to the desired carrier type and concentration. But if you look at this diagram here, you see ZT plotted as a function of carrier concentration. And it shows that in order to actually maximize ZT, we need large and controlled carrier concentrations approaching around 10 to the 19th per centimeter cubed, which is actually quite large. And in kind of conversely, in the lab, in reality, our experimental collaborators were finding that only around 10% of the materials they would try to synthesize could actually be doped in the laboratory. So there's a need to incorporate screening for dopability into our computation guided search as well. Okay, so let me give you an example of some of our screening approach at work. We'll look a little bit at one family of materials, which are these ordered vacancy compounds, or OVCs. OVCs are a subset of diamond-like semiconductors, except that whereas a diamond-like semiconductor, each atom has this nice sp3 type tetrahedral coordination. In these ordered vacancy compounds, there's a regular ordered array of vacancies that disrupts somewhat that network. This is also called the defect chalcopyrite structure. In these ordered vacancy compounds, the telluride versions in particular appear to have low thermal conductivities, but then the benefit of this diamond-like or sp3-like bonding also tends to be associated with very dispersive valence and conduction bands and generally good carrier mobilities. So they're good candidates for thermoelectrics, which is why we decided to focus our search efforts on these. Ordered vacancy compounds in general, they come in a variety of different stoichiometries, but in any case, we decided to focus on the three prototype structures illustrated here. We have the 158 stoichiometry, the 124, and the 214 stoichiometry. And to carry out this search, what we've done within these stoichiometries is we introduce isovalent chemical replacements to these prototype structures to create these hypothetical ordered vacancy compounds of various chemistry. So using these chemical substitutions here, we end up with 54 total candidate materials. Okay, so this slide here shows the computational workflow that we applied. The work I'm going to show here was done by my student Jiaxing Chu here at Illinois. And what we do is we start with that candidate set of chemistries, and then we run them through this set of filters. The filters are applied in a strategic way where the least computationally expensive screens are carried out first on the largest number of candidates. And then the most expensive screens are carried out towards the end when the number of candidates has already been filtered down. So in our case, the workflow starts with a structural relaxation for the compound. We then make sure that the compound has a non-zero gap. We then assess its thermoelectric performance through the quality factor beta. The most promising candidates there are run through a convex hull analysis to determine their thermodynamic stability. And then the final most promising set of compounds are checked for their dopability. Okay, so this slide shows some of the results of our assessment of the quality factor beta for our 54 OVCs. The diagram on the left shows beta for N-type doped, and then on the right for P-type doped semiconductors. The x-axis shows the predicted lattice thermal conductivity, and the y-axis the predicted carrier mobility, electrons and holes. So again, good thermoelectrics here would appear on the upper left. One observation here, which you can see just from comparing the scale of the y-axis for electrons and holes, is that N-type ordered vacancy compounds are predicted to have better thermoelectric performance than their P-type counterparts, largely due to these larger predicted electron carrier mobilities compared to holes. And then the points on this plot are colored according to the band degeneracy for the carriers. And again, the size of the circle indicates the value of this quality factor beta. Just for reference, this circle here shows beta for lead telluride, which is a classic thermoelectric material. And so any circle that is larger means that we predict that this material has the potential to show better thermoelectric performance compared to lead telluride. Okay, and then at the next level of the screen, we assess the thermodynamic stability of the compound, meaning that we try to determine whether the compound is thermodynamically stable or likely to decompose into competing secondary phases. So the top row here shows our selenium-based compounds. The bottom row shows our tellurium-based compounds. This first column are the 214 stoichiometries. The middle column are the 124 stoichiometries. And the one on the right are the 158 stoichiometries here. And then the color bar indicates the distance to the hull that we predict for the material. So anything that's yellow is a compound that's predicted to be on the hull or stable. And the more blue it gets, the more likely we believe it is not going to be a stable compound. So if you look at this, you'll see that all of these 1, 2, 4 ordered vacancy compounds are predicted to be stable. And in fact, these circles here mean that the chemistry is an already experimentally known or reported chemistry. So in this case, all these 1, 2, 4 compounds are predicted to be stable, and in fact, they're experimentally known. And then meanwhile, the 214 phases and the 158s, we've rediscovered some already experimentally known phases, but then we also predict a few more to be stable that have not yet been reported. So it may be the case that some of those families are somewhat underexplored. Okay, and this is my last slide. Here is where we move on to the dopability of the materials. We take the most promising compounds, the ones that show a good quality factor, and are either predicted to be on the hull or not too distant from the hull. And we determine their defect chemistry through defect calculations. So I'm showing 2 examples here in the 124 family. If you're not used to looking at these defect formation energy diagrams, then what you should focus on for each compound is where this tent here appears, which is made up of the lowest energy donor and acceptor native defect. This is what will limit your P-type and your N-type dopability. And so if the peak of this tent is close to the conduction band maximum, like the one on the left, we can expect to achieve a good N-type carrier concentration here. And then alternatively, for example, for this material we tried on the right, this one turned out to be not so good. The peak of the tent is closer to the middle of the gap, and so we don't think this one will be as dopable. Okay, so I hope this provides an idea for some of the approaches we've used in the past on the US side of the collaboration. I will quickly pass the microphone back to Ibrahim here, who will describe some of our collaborative plans.
I need to remind you that we need to finish very soon. We certainly appreciate
Ibrahim,
Yes.
you can go quickly, right?
Okay, thank you very much. Thank you, Elif. Based on the experience from the part of the African team, move to the next slide, and also the US team, we found out that the two teams have something in common, which is studying material for thermoelectric applications. So over the years, African team have been studying half-Oscillate compound, while the US team are also using series of computational tools and resources to find good material for thermoelectric application. So we are trying to combine these two concepts together to form a kind of a collaboration. And we can see that the African team is coming with idea from Oscillate compound, while the US team is coming with computational concept and techniques for screening material for thermoelectric application. And that leads us to a topic which is computational assessments and discovery of material. So our collaborative plan is just to combine our expertise in the compound that we have been studying and the screening techniques used by the US team. So we have two plans at hand at the moment. We are interested in looking at the vanadium, cobalt, germanium, and niobium, cobalt, silicon, which has just been predicted to be a good thermoelectric materials. So we tried to look at the thermoelectric material descriptor, which is beta for the two compounds, and also try to predict the N-type and P-type of thermoelectric performance through doping of these two half-Oscillate compound. And we want to see if doping this material, can we possibly increase the power factor and reduce the lattice thermal conductivity, and in the process increase the figure of merit. So our second plan is to use the screening technique of Elif's group to screen some elements if it is possible for us to have good thermoelectric from half-Oscillate alloy and full-Oscillate alloy from this series of elements. Next slide. So our preliminary data on these two compounds, we try to look at the dynamic stabilities of this compound, and we found out that the photon dispersion of this compound give us a positive frequencies, which means that the materials are stable. And also in the previous work in 2019, these materials, they predicted that they have a very high lattice thermal conductivity. Next slide. Next slide, Elif. So we actually use the empirical method developed in, put together in the group of Elifs to study or to compute the quality factors of these two compounds. Using this technique, Elif have discussed this in some slides about 3 or 4 slides ago. So move to the next one. Let me just show the result. So our preliminary data as regards to these two compounds, using this concept from the Elif group, we found out that this material, if you look at this table, we have the first two columns, which shows the power factor, the beta for the P-type and the N-type of this material. And we can see that the P-type has a very high beta value, as Elif said in the screening techniques they have in their group, that if you have a very high beta value, that shows that the materials could be a very good thermoelectric materials. So in this case, we realize that these two materials will be a very good P-type materials, and we just have this data for our system, the effective mass, the dose effective mass, which is in the third column, and which is for the valence band, and for the conundrum band in the fifth column. Then we have the carrier concentration, and we found out that the predicted value from these techniques actually has a very good agreement with what was reported in the previous paper. And I think I have to pass to Elif to give a photo thank for bringing us together for these collaborations.
Okay, so I have to insist that we've finished soon, even though it's wonderful to hear about this.
Thank you, everybody. I will just leave these acknowledgements slides up here. Let me just say very much thank you to Richard, especially for introducing this group, and thank you to the workshop organizers and the USAfri program.
Super. You did a great job. And it's just wonderful to hear about the collaboration. So you gave me some credit. The reason that I knew about this was assessment that I had learned, particularly from Adetunji, about the interest in thermoelectrics and Oscillate alloys. So we have a few moments for questions. It's my impression that the thermal conductivity is really hard to calculate. It depends upon disorder and all that kind of stuff. Did you take that into account?
Yeah, good question. I can speak about the way that it's done for in this quality factor, and then maybe from the Africa side, the others may want to comment on some of the other techniques that they've used. But within this idea of this quality factor beta, the transport model for thermal conductivity is actually relatively simple. It's based on like a Debye-Callaway model. And so there's a general expression that's used to describe phonon-phonon scattering, and then it's completely unaware of disorder or defects or things like that. So that gets ignored at this level.
Okay, thank you. If anybody else wants to ask a question, please unmute yourself.
There's a question in the chat from Michelle Cote. Michelle, do you want to say it out loud, or do you want me to read it out? So I can just read it out. So it says, can you give us an idea of the codes used and the functionals, etc.?
Sure. Is this for Michelle for which part?
Oh, African group or the US group?
Okay. Go ahead, Adebayo or Dele, would you like to comment?
Well, I can just answer that quickly. The African team, we are well familiar with the Quantum Espresso package. And of course, this is not the only package that we use. We also have the Bootstrap package, which actually allows us to calculate all these thermoelectric properties. Thank you.
Thank you.
Thank you. Yeah.
Are there other questions or comments? So we're actually doing all right. Fortunately, we built in some breaks, and so if there are no other questions, we can take a break for 5 minutes, and we'll be on schedule.
So Richard, please, can I ask a quick question?
Oh yes. Oh, please.
Sorry. There are some people who claim that bismuth materials do very well as thermoelectrics. Do you have any comment about this and why this may be so?
Elif, do you want to answer that, or you want me to answer that?
Why don't you start, Adebayo, and I can chime in.
Yeah, okay. If I understand the question very well, you want to know why bismuth material or bismuth-based materials perform very well as thermoelectrics. Is that the question?
Yes, exactly.
Yeah. On our part, we have not actually worked on bismuth material based, but of course, I can tell you that there are certain things that you have to look for if you want to make a material be a good thermoelectric. Bamidele has mentioned that that you must have a high ZT. ZT, I mean a high figure of merit. Okay, so it could be that bismuth-based materials actually possess low thermal conductivity, and then making the power factor be very high, such that you can have the ZT very high also. Thank you.
Okay. Okay.
Yeah, and I'll just add to that it's true. A lot of our best thermoelectrics are often these like bismuth telluride or bismuth antimonide. So it's true, we do see some of these elements appearing over and over again in these materials, and I think it's a combination of a couple of different factors. Remember, you're always looking for a low thermal conductivity, but wide dispersive valence or conduction bands so that you can have high carrier mobilities. And I think that a lot of these, I mean, this is a bit of an oversimplification, but bismuth, lead, tellurium, these compounds that we're often seeing in thermoelectrics, they tend to be, you know, heavier atoms with low phonon group velocities, so low thermal conductivity, and then, but also they have a wide set of bands associated with them. So you can get, you know, dispersive bands, large carrier mobilities. That seems to be the trick. It's more complicated than that, of course, because there's this interesting connection to like topological insulator, spin orbit coupling effects kind of kick in with these heavy elements also, and that affects the shape of the bands as well. So there's a lot of interesting parallels there. And you know, the other thing that this reminds me of, Richard, is in your question about defect scattering. I think a lot of our best thermoelectric, so we have these pristine materials, lead telluride, bismuth telluride, and they're good thermoelectrics. But I think if you really want to fine tune all your properties, you probably are going to need to look to some kind of targeted alloying or mixing of different materials so that you can really tune in the desired features you want, like band degeneracies, heavy atoms. Actually, we benefit from disorder or defects, because sometimes, I should say, because that can really suppress thermal conductivity as well.
Okay, thank you.
Thank you.
One more quick question. Have you looked into like different dimensions, like maybe 2-dimensional versus 3-dimensional? Is one better than the other, or?
That's a good question, Omololu. At least in my work, I've stayed pretty close to only bulk materials. Somehow they are already chemically rich and diverse enough in the types of structures we get from them that my interest has just been focused in that area. I know there's a lot of work thinking about 2-dimensional materials for thermoelectrics as well. And I think that's really interesting, because the nature of phonon modes in 2D, where you have flexural modes like this, becomes kind of interesting. 2D materials can often have high thermal conductivity, so this makes it difficult. But yeah, there's a lot of interesting work going on there. The work that I've done has been largely with synthetic chemists who are synthesizing bulk 3D materials.
Okay. Thank you very much.
Thank you.
To everybody, yeah.
Okay, so it's time for us to move on. This is wonderful to actually give a talk that educates us on a set of problems and shows in the collaborations. Thank you very much. Let's take a break for like 3 minutes, and we'll be a little behind schedule, but this is remarkable for the start of the Zoom conference. We're almost on schedule. So Yang Sun, are you ready to go?
Yes. Hi, Richard.
Hello there. Let's take a couple of minutes to let people get themselves organized if they wish. And
meanwhile, maybe I'll just share my screen and
okay,
it works well.
Okay, perfect. So we'll be ready to go.
Yeah. At the same time, everybody, please note that we'll have a breakout session afterwards. So if you want to talk more
yes,
with Professor Adebayo, Professor Elif, Professor Adetunji, Winfred about their work, you will have a chance to meet with them and talk to them, and I will also have a chance to torture them with my questions. That's a joke. Okay, but we'll be meeting with them after. You can meet with them in the breakouts afterwards. You can also meet with Yang Son, who will be talking soon, and with Victor and Gamakis, who will be talking soon. You can meet with them during the poster session. We'll talk more about the poster sessions later on, but you can meet with them afterwards to ask them as many questions as you would like to ask them, and maybe develop collaborations with them also. Thank you.
Okay, yes, so thank you. I'm very glad to be reminded. If I understand right, then we will not ask for questions. We'll go right between talks, and then you'll have a chance to ask questions after the three short talks today. And each talk we have to keep time so that we actually leave time for questions. So I think we've had a very short break, and we're ready for Yang Sun to start. And we asked the other speakers in this session to be ready to go.
Okay, so should I start?
Yes, go ahead.
Okay, great. So hello everyone, very happy to present our recent work on the Fe iron-rich FeO crystal phases at the Earth's core pressures. So this is to showcase how the computational physics and especially DFT calculations can help to elucidate the nature of Earth's materials synthesized in the laboratory. So first, I would like to acknowledge my co-workers, my supervisor, Renato Winskovic, and from Columbia University, Kaiming Ho and CZ Wang from Iowa State University, and experimentalist Afuni and
You are muted. Unmute yourself.
Yang Sun.
Okay, is it better?
Yes.
Okay, yeah, somehow. Okay. All right, so hello everyone. Sorry, I'm very happy to present our recent work on the iron-rich FeO crystal phases at the Earth's core pressures. So this is to showcase how the computational physics and the DFT calculation can help elucidate the nature of Earth material synthesized in the laboratory. So first, I would like to acknowledge my co-workers, my supervisor, Renato Winskovic from Columbia University, Kaiming Ho and CZ Wang from Iowa State University, and Afuni and Jing Liu, who performed advanced experiments at our funding agency, National Science Foundation. So the Earth has a layered structure, and the core is its major part. So the core contains two regions, a liquid outer core and a solid inner core. So it is in a very large pressure range, ranging from 136 gigapascal to 364 gigapascal from the core mantle boundary into the inner core. And the iron is the major element in the core. So the solid part is generally believed to be the HCP iron, while the outer core is mainly the molten iron. So, but there is also other light elements in it. So if we look at the iron density under the core pressure, it has a clear difference compared to the preliminary Earth model, which was constructed from the seismic data. So if we plot the most recent data of the iron liquid and the iron HCP as a function of the pressure, so here dashed line and solid line is just the possible temperature range inside the core. So you can see that the outer core has a 10% mass difference to the Earth model, while the inner core has around 5%. In order to explain this density deficit, it's generally believed that there exists light elements such as oxygen, sulfur, silicon, carbon, even hydrogen in the core. So therefore, it is crucial to understand how this light element coexists with iron at high pressure temperature conditions. So the distribution of the light elements in the inner core and the outer core, solid and liquid parts, mainly depends on its partition. So why it's still very challenging to measure the actual phase diagram under the core conditions. But after the many years calculation and experiments, people have proposed a phase diagram between iron and a light element at high pressures. So here is some proposed one at 330 gigapascal, which is in the core boundary. So if you look at schematically these figures, you can see that the sulfur and the silicon is quite similar. So they all mix with HCP iron and forms a solid solution on the iron-rich side. But oxygen is a very special case. So it's believed that there is no solubility of oxygen inside the HCP iron at the inner core condition. So there is only pure iron and the iron monoxide as the end monomers. So this conclusion was mainly based on the so far there is no iron-rich FeO compound has ever been reported yet. So recently, actually, our experimental colleagues actually find that it is possible to mix the iron and iron oxide to form new phases. Here, they first compress a mixture of iron and iron oxide to 220 gigapascal in a diamond iron cell. If they laser heat it to around 2000 Kelvin, actually nothing happened. Once they reach more than 3000 Kelvin, they find a large decrease of the iron peak and FeO peak. Meanwhile, some new XRD peaks appeared, which indicates the formation of the new phase. And the key feature of this new phase is that it shows a multi-peak in a very narrow 2 theta range. So in order to solve this phase, they first try to match it with all the with database. Unfortunately, it cannot be solved by any known compounds. So here to help, and we performed a crystal structure prediction in order to identify possible iron-rich FeO phases. Here we use an algorithm, so-called adaptive genetic algorithm with DFT calculations. So the key idea of this algorithm is to obtain no energy crystal structure with the only information of the chemistry. So this algorithm combines ab initio calculation and the semi-empirical potentials for efficient crystal structure prediction. So because of limited time, I cannot go to detail of this algorithm, but the method was mainly developed by whole group and the Winskovic group to solve the complex mineral materials. So here is some results. So here's we use AGA to obtain all these iron phases, iron oxide phases in between HCP and FeO. So this is mainly on the iron-rich side or oxygen pool side. So in contrast to previous proposed FeO phase diagram, we actually identified many possible iron-rich FeO compound at 215 gigapascal. So in order to evaluate its energetic stability, we computed the formation enthalpy using iron and FeO as a reference. So each data point represents one crystal structure. And based on this data, we constructed this convex hull, which represents the ground states. Now let's look at some of these structures. So if we look at this Fe iron 3 oxygen, it actually is a hexagonal lattice, and this is its projection. So AB is 120 degree. And this is iron 2 oxygen, iron 3 oxygen 2, iron 4 oxygen 3, iron 6 oxygen 5. As you can see, all these ground state actually forms a hexagonal lattice, and the iron and oxygen atoms is close packed to form this complex layer sequence. And if we mark all these similar hexagonal lattice in the structure search results, actually you can find it's quite large populations. And recall that iron HCP and iron FeOBH is also similar, has also similar pattern. So therefore, it indicates that these iron-rich compounds are just by redistributing the iron and the oxygen in a close-packed hexagonal lattice. And now let's compare these new structures with the experimental XRD. So first, we look at one of the ground state Fe3O. It provides one of the peak of the XRD. And this is another ground state Fe4O3, which matches another part. And we also looked for some metastable phases, and you can see indeed, they can match part of this XRD. And this is small difference of these XRD peaks are all corresponding to different stacking of the FeO in the hexagonal lattice. But the question remains that if there is a structural model that can describe all these phases. So in order to achieve that, we perform a reverse Monte Carlo simulation to construct a large structure to match the XRD. So we use this mean square deviation between experimental XRD and the simulated XRD as a criteria to select structures. So in detail, we actually build a large supercell and randomly swap the layers and change its chemistry. And we use the Monte Carlo strategy to accept the swapping rate. And we have no restriction on any FDO ratio during the simulation. And indeed, with this simulation, we actually find a very large supercell containing 42 layers. And this supercell with this specific layering can match all these unknown XRD peaks. It is a metastable state, but the energy is very close to the convex hull. So to further understand this large supercell, we analyzed its chemistry and structure. So as you can see, is that while it's overall 2-1 composition, but actually it has very strong chemical fluctuations along these C directions. So this is quite related to experimental conditions that it was synthesized at high temperature with very short time laser heating. And the cooling process was very fast. So the kinetics can be quite limited to fully reach the equilibrium. So this supercell actually does not show this long range structural order on these C directions. But when we indeed look in detail of this stacking, so we can actually identify the domains. So this dashed line actually shows this direction of this domain flows. So this domain size is around 20 atom layers or around 30 angstrom, and it all has a different stacking sequence. So this forms kind of medium range order, and this kind of medium range order actually contribute differently to the XRD. So as you can see, this domain A, if we isolate it and calculate its XRD, it mainly contributes this 2 peaks. And if you look at the domain B, it contributes to somewhere here. And then this combination of this A and the B and their interference actually give rise to this multi-peaks and smeared in this region. So finally, with experimental refinement, this structural model well displays the experiment. So we believe it proves that at the laboratory condition, the oxygen can start to mix with iron at iron-rich site and forms this layered close-packed structure. So in summary, experiments identify possible reaction between iron and iron monoxide at 220 gigapascal. We use this adaptive genetic algorithm crystal structure prediction to identify a number of low energy iron-rich phases on the high pressure. So this iron-rich oxide all share a common close-packed hexagonal lattice. A supercell with iron-28 oxygen-14 phase can well match all the unknown peaks of experimental XRD, suggesting that existence of iron-oxygen solid solution in this close-packed hexagonal structure. And our results indicate a large amount of oxygen can be incorporated in HCP iron at all core conditions, contrary to previous understanding of FEU chemistry at core pressures. Thank you very much.
Thank you, Jan, for a clear talk and for finishing on time. That's great.
Thank you.
So is our next speaker here, who I think is Victor? Is that correct?
Yes, Victor Meng'wa is our next speaker.
Okay.
Hi, Victor.
Yes, okay, I'm there. I'm trying to share the screen. Yes, so can you see my screen?
Yes, we can see yours.
Okay. Okay, thank you. So welcome everyone to this talk. The title of my presentation is DFT Study of Water Photo Oxidation at copper oxide nanostructures on the Anates 101 surface. So currently, the most recent report on the recent report, the 2020 Global Citrus Report, shows that at the moment we rely on the solar. It's only 12.8%. We have a reliance of about 2.8% on the solar PV modules, and therefore, if you look at it, we still we still rely so much on the non-renewable electricity at more than 70%. Solar energy is very abundant. It's clean, it's renewable, and is inexhaustible. 1 hour of solar radiation is enough for annual world consumption. Now, why should we split water? We split water because one is why should we split water to hydrogen and oxygen? That water is clean, hydrogen is clean, storable, and portable. It's also high density and an efficient fuel, and it will produce hydrocarbons from CO2. Now, in this particular process of splitting of solar energy and harvesting energy from the sun, it's usually convenient to store this energy. And one way to do that is to convert this into chemical energy. And we do this using a photo electrical splitting cell. And this is what you can actually see from here. You see that this cell has an anode and a cathode. On the photoanode, when we radiate with the solar radiations, we get electrons to the CB, which actually are transferred. You can actually see from here, they're transferred to the cathode. Then holes are actually left on the anode, which oxidize water to produce oxygen. So we have an oxygen evolution reaction on the photoanode, and then a hydrogen evolution reaction on the cathode. Now, usually the oxygen evolution reaction requires a large over potential, and therefore it's usually the major obstacle in this process. Now, for us to do the water splitting, first of all, we did the absorption of water on the coupled oxides on the coupled cuprous and cupric oxides. And what you can see here that on Cu2O TiO2 nanowires, water prefers to absorb molecularly. Water prefers to absorb molecularly, both on both oxides. On both oxides, they prefer to absorb molecularly. I've just shared these are the absorption energies that we have on the side. Similarly, on the cupric oxide, this case is different. Water here is partially dissociated with OH at the bridge side between Ti and the copper atoms on the nanowire, and the hydrogen is actually on the CuO. Similar to the metastable structures, the structures that the metastable structure, which is the structure in B. Now, the approach that we used this particular calculations of the North scope approach, which makes some assumptions, and one of the assumptions that the system is in equilibrium with the standard hydrogen electrode, that the photo-generated electrons of the photoanode are emitted by an effective bias with respect to the standard hydrogen electrode. Now, we did this calculations also. I will show, when I show you the results, I will show you thermodynamic stability results under the PEC conditions. And this we carried out by calculating the surface free energy using the formula that I've just shown there. And the surface free energy of water absorption species, which in this water absorption species, in this particular case, which are the hydroperoxide species, the hydroxyl species, and the atomic oxygen on the copper oxides that are mounted on TiO2 with respect to the bulk copper is determined from this particular equation that I've just shown here. This equation is actually extracted from the calculations of the surface energy that we have here. In this particular case, in this we have 1/2A, whereby A is the area of the surface, then G is actually the Gibbs free energy, then minus the sum of Ni is the number of the atomic species, and mu I is actually the chemical potential, which is actually a function of the bias. Is actually a function of the bias. So these are some of the results that that we got. This is from the pristine anatase 101 surface. Basically, this one was just to give us a baseline comparison with what will happen with the coupled oxides. So if you look at this, if you look at what we have here, we see that for nomenclature, what it means here is that this is this is S1. This means that this is this pristine TiO2. Then 001 means that the one at the end means that this is an hydroperoxide species. When we have one at the start, it means the atomic oxygen. Then we have one at the middle. Then it means that these are hydroxyl species that we have on top of TiO2. So you can, what we see is that the hydroperoxide species is more stable on TiO2, while the least stable is the hydroxyl species, that is the OH on TiO2, and the reverse is true when we extend this when we have a zero bias. Remember that this bias is from 1.5 volts to 5 volts. So if you stretch this further to around zero bias, then we'll have the reverse. On for the oxides now, we have two oxides here. We have the two oxides of copper on TiO2. S3 stands for the CuO over TiO2. Then S2 stands for the Cu2O over TiO2. So we see that at effective bias, which is actually equivalent to the energy, gap of pristine TiO2. We see that all the species, all the water oxidation species on CuO TiO2 are more stable compared to those ones on Cu2O over TiO2. Again, when you go to the zero bias, again the reverse actually is true. The reverse is true. So so what if we look again at this, you will see that we have I consider two sites: a site on the coupled semiconductor oxides. I consider two sites. One site is where we had the species basically on TiO2, and another one on the copper oxide species. That's why you can see that we have S32 like 001 and S32 and S31001. So it means one is on the cupric on the copper oxide, and another one is on TiO2. So OH species again is stable again in both cases, and that's at effective bias. But OH species again will be stable on the at zero bias. It's again Cu2 over TiO2 that the OH species on these two on Cu2 TiO2 again the most stable. Then so under photoelectrochemical conditions and at effective bias, we have seen that oxidation species on CuO TiO2 are more stable than on Cu2 or TiO2. But at zero bias, I've mentioned that the reverse is actually reversed. Now, what we know is that CO2 experiences superficial oxidation reaction to CuO, and again, the most stable species OH, which is actually at the interface between Ti and the copper atoms. Hence, we have a cooperative behavior of the two materials. Now, we already know this reaction again is...
I need to remind you to finish soon. I forgot to give you a warning sooner. Okay. Okay, Prof. So this is
this is a photooxidation reaction whereby we have A, we have hydroxylation, we have dehydrogenation, then we have formation of hydroxyl species, then formation of the oxygen. So we have A, B, C, and D. Now, if you do the photooxidation reaction, if you calculate the overpotential, the overpotential is calculated from getting the maximum of the Gibbs free energy of the reactions that are just mentioned, A, B, C, and D, minus 1.23, which is actually the equilibrium potential. Now, if you do this particular calculation, and remember that this is the photooxidation cycle, if you do this kind of calculation, you can know that the Gibbs free energy, which is the highest, like for pristine anatase 101 surface, is 2.62 electron volts, and you subtract and minus 1.23, you get that the overpotential is actually 1.39 volts. Now let's see what happens when you have the coupled oxides, like Cu2 over T the overpotential is actually reduced from 1.39 to 0.77 and 0.448, and this is a significant reduction compared to the 1.39 that you get in the pristine TiO2. Now, similarly, if you do the same I'll explain that. Similarly, if you do the same to Cu or TiO2, you again the potentials again reduced to you'll obtain potentials of 0.66 volts and 0.96 volts, and this occur we realize that the potential determining steps are at the hydrogenation of the adsorbed hydroxyl group. Now, the main reason why we have this is because remember that in the pristine, the potential determining step was actually at the hydroxyl, at the OH. What we have, what these oxides do, what
Victor,
coupled oxides
we need to conclude. We need to go to the next talk.
Yes, what coupled oxides do is that they stabilize the OH. The OH is actually stabilized, and that's why we have a reduction in the overpotentials. And so from what we have just seen, we have realized that that under that overpotentials are actually reduced when we couple the copper oxides with the TiO2, and also they also shift the overpotential determining step. Thank you. Thank you. That is the end of the talk.
Okay, thank you. Thanks for educating us with a good talk. So now we need to move to, oh Lord, the speaker. Sakata, is that correct? Are you ready? What's happening?
Yes, Gamakis. Victor should share. Gamakis, can you share? Okay. Gamakis, are you there?
I think he was online earlier.
Yeah, I saw him too. Yeah, I saw him and I even told him. Let's wait a few minutes.
We could start questions for the previous two speakers while we're waiting.
Yeah, good idea. I think that sounds exactly right. Thank you, Sinead. So do we have some questions for the speakers? Yang Sun, are you there?
Oh yeah, I'm here.
Yes. What difference does it make to the world if a bunch of oxygen is in the core?
Very good question. So, okay, maybe I should share this screen again. And I would say that, so people are trying to figure out, oops. Okay, here it goes. Right. So the major question to answer is what contribute to this density and how this different elements partition in this liquid side and the HCP side. So, and the current major data is from the seismic observations. So there are actually really no any other knowledge to help understand this question. So it's kind of guessing. So oxygen was firstly proposed as a major elements due to the Earth's histories at starting from the very beginning. But later on, people find out that this oxygen seems cannot to mix with iron in the lower pressures. So this knowledge was, this kind of understanding will stand there for almost quite a few decades. And just very recently, we start to realize that actually oxygen can also mix with iron in the solid form. So this would bring quite a bit new chemistry to in order to model the inner core, especially its seismic properties. Yeah.
Ah, good. Okay, thank you. Are there some other questions for either speaker?
Okay.
Afternoon, I have a question to Yansu.
Yep.
I want to know what is the convergence criteria on your DFT algorithm, and when it's not converged, how do you mix the density to re-enter inside the chain? The convergence criteria.
The convergence criteria of DFT calculation. For the self consistency, we usually use 10⁻⁵ electron volt, and for the force convergency, we usually use 0.01 eV angstrom. Yeah.
Okay. So since Gamakis is here.
Oh, sorry, did you say he's ready?
Yeah, he's here. So
Gamakis
is
ready.
The screen. Gamakis, do you want to share your screen?
Ah, it looks like well, I don't know.
Okay. Or do you want me to share your PDF and then you speak?
Are you speaking? I cannot hear you.
You should unmute yourself. Unmute yourself.
Ah.
Yamakis, you should unmute yourself. No, Gamakis, we cannot hear you. You should unmute yourself.
I think he's unmuted, but so quiet. We can't hear.
Oh.
Ah.
We're
already in the question and answer session, so perhaps we should stop now and see if we can work in your talk later.
Okay, okay.
We see your face, but can't hear you.
Yeah, we can't hear you. So you can try to make a recording and send it to us, or we can try to practice and see that it works next time. Okay.
Okay, or in the poster session or something.
Yeah, or in the poster session. Yeah, I have a room for you. Cathode materials for batteries, so you can go there and discuss with people there. Okay. Yeah, because we can't hear. Yeah, because we can't hear you. Okay. So I think we should take questions now, Richard.
Okay, okay, let's everyone, do you have questions for Victor or Yang Sun? Oops. Oh. Sorry, if I'm not unclear, but at any rate, we still have a little time in this panel session. So does anyone have another question?
I have a question, Richard, for Victor.
Yes, good.
Victor, I know you didn't have a chance to tell us the conclusions to your work. Do you want to have a minute now to do it?
Thank you.
Okay, so
You can just share your screen, maybe the last slide.
Okay. So
Good.
Yes. So at zero bias, water absorbed molecularly on Cu2O, TiO2, and dissociatively on CuO TiO2 system. So the absorptions of water on these two oxides on the two oxides of copper on TiO2 is actually not the same. Now under photoelectrochemistry, and this goes with this supported by our previous work on the electronic structure of these two oxides. Now under photoelectrochemical conditions, CuO TiO2 system is more stable than Cu2TiO, contrary to what happens in the absence of electric bias, because in the absence of electric bias, the reverse is actually true. Then the copper oxide modified the overpotentials, which we actually saw that they reduced to 0.48 volts for the Cu2 or TiO2 system, and 0.6 for CuO TiO2 system, which is a sub-decrease compared with the pristine TiO2, which had an potential of 1.39 volts. And this is actually due to the stability of the main reason for the diesel potential, which is actually due to the strong absorption of the hydroxide species on the copper titanium system, on the copper titanium modified system. And if you assess and if you look at the structure of the structure of the two systems, it actually supports this kind of conclusion. Then the potential determining steps are again different. For the pristine TiO2, it's at hydroxyl formation, while for the copper titanium system, it's mostly at the dehydrogenation of the absorbed hydroxyl in most cases. That's not in all cases, and this one takes place mostly in that this is the second step. This is the step B in the water oxidation reaction, while the hydroxyl formation is actually in the first step. Then lastly, that there is a synergetic effect from the addition of the nanostructured copper oxide to titanium, and this contributes actually to the reduction in the overpotential. And you can actually see that the most stable species that's the effective bias actually is the absorption actually takes place between the copper oxide, the nanowire, and the TiO2. So that cooperative behavior actually contributes to the stability and the reduction of the we can see that it also mainly to contribute to the reduction of the potential. Stability I've talked about is because of the stability of the hydroxyl species. So I want to just acknowledge my co-authors, Nicola Seriani, Sandro Scandolo, Georgia Molo, and Nicholas Macau. Then thank you for your audience.
Great, nice to see the conclusion. Thank you.
Yes.
Are there other questions? So, Omololu, it's time to set up these breakout rooms. Are they already set up?
No, the breakout rooms are not set up except for the speakers.
Well, that's what I meant. I'm not fully sure how this works, but we want to have the opportunity for people to ask questions. We can just stay where we are right now if it's.
Please,
if it
I have a
better.
question. I have a question to Victor. Please,
Yes.
Victor,
Yes.
How do you discover interaction between water molecule and your system of oxide, copper or oxide titan? What are the parameters of your potential are taken in account this interaction in your potential?
Okay, just yes, again, please. Yes, just ask again a question, please. I didn't get it clearly.
Victor, are you speaking? We
Ask
cannot hear
again the
you.
question, please. Yes, I am not speaking. I did hear the question properly, so I had asked him just to repeat the question.
Oh.
All right, right on the chat.
Well, oops.
Yeah, my question is to know, how do you discover interaction between water molecule and your system? You say that you use oxide, copper, or titan oxide, or oxide titan. What are the parameters on your potential that are taking into account this interaction between water and oxide, copper, and oxide titan in your potential?
Okay, so the interaction of the water molecule with the either TiO2 or the nanowire. I think that if that is what I got clearly. Okay, we didn't deeply go into those studies. We limited our work on just adsorption only, and our main concern was that we prepared different configurations of the water molecule on top of the oxides, and did Lux calculations, and found the most stable system out of those. That's what we used to proceed on with the calculations. But the studies of the more insights into the studies of water on top of that, we did not do it. We did that, and then we did again relied on some literature that we'd already read on water on TiO2 and water on the copper oxides. So that's it.
Okay, I think we're just staying in this big room with everybody, big Zoom room.